this what's linked to the inductor, self-inductance here, carries the current. This once is changing, the real induced magnitude is given by VI. The constant current goes through an inductor is energy stored in the magnetic field. This energy is how much? Li square. You know that number? In the case of capacitor, it is half C square. Here it is half Li. And the energy density in the case of capacitor, half epsilon half E square. Here, energy density is V square, right? Not. You are coming across those relations already. So we will try some problems. You know that when a number of inductors are connected in series, of course, provided they don't interact with each other, there is no interaction between the magnetic flux of this, not be linked with this. When you have a number of them connected in series, the effective inductance is given by. When they are connected in parallel, the effective inductance is given by. You know these relations, huh? Use those relations to write down. To begin with, we'll take up some simple problems and then go into some problems. I have two inductors in that case. L1 and L2 connected in parallel. And current enters this. Question is, what is the expression for current to L1? Current to L2. How do you? How can you arrive at? How can you arrive at?
Say total potential drop across that is I into the effective inductance L1 L2 by L1 plus L2. That is same across both the wires. So I1 into L1 should be equal to that and I2 equal.
Another way of putting it is, because they are in parallel, can you not put it like this? Or after all, L1 and L2 are constants. Correct? Integrating. This is one relation. Another relation is substitute for I2 say I minus I1. Get the expression for I1. Similarly, get the expression for I2. So what is the final? I1 will be equal to clear? I1 is equal to main. All it is this main current into inductance in the other branch divided by. I2 is main current into inductance in the other branch divided by. Yeah.
So here I1 and I2 are very continuous. And after some time, say once di by dt becomes 0, then both are like short circuit. then which side will prefer to go?
Once steady state condition is reached, you say this acts like a
Short.
circuit, it offers zero resistance, this offers zero resistance. But the division is remaining the same.
It will still be I1 and I2.
Yeah. Let's take a problem and see how we current I enters here. The values of inductances are L1 equal to 1 millihenry, L2 equal to 2 millihenries. Okay? Find the ratio of fluxes. Find the ratio of currents. Find the ratio of energy stored. Come on. First, what is the ratio of fluxes? Ratio of fluxes is, yes, 1:1. See, phi1 by phi2 is L1 I1 by, take current in this case, I1 current in this sense. I will agree. But we have already said that L1 I1 equal to L2 I2 when they are parallel. So phi1 is to phi2 is 1 is 1. Okay, what is the ratio of currents? From this you can see I1 by I2 is equal to phi1 by phi2 into L2 by L1. Phi1 by phi2 is 1:1. What is L2 by L1? 2 by, we have said this is 2, this is 1. So 2:1. What is the ratio of energy? The ratio of energy is U1 by U2 is equal to half L1 I1 squared by half L2 I2 squared, which is L1 by L2 I1 by I2 the whole square. How much it comes to? 2. Voilà. Next. For the two non-interacting series connected coils of inductance is L1 and L2, find the ratio of fluxes. Find the ratio of fluxes. Find the ratio of energy in L1 and L2. Come on. L1 is to L2, exactly. Ratio of energies? Because they are in series, same current is flowing, no? So phi1 by phi2 is L1 I1 by L2 I2. I1 and I2 are equal. So phi1 by phi2 is L1 by L2. What about the energy? Half L1 I1 squared by half L2 I2. Clear? Simple problem. You know, if you had a coil of self-inductance in a circuit, what is the behavior of this coil? It tries to oppose any change in the current flowing through it. Correct now? If there is any change in the current in the coil, immediately reacts by developing a back EMF across it. Greater the rate of change of current through that, greater is the EMF. Correct now? So using this idea as well as Kirchhoff's laws, you can analyze the circuit containing an inductor, a resistor. I have a inductor of inductance L and a resistance. Of course, here this R may be a separate circuit element, or it could be the resistance of the windings of this coil. So this is really a practical inductor that you have considered. There you are dealing with all ideal inductors. Now when you put this in contact with this, what happens? At the instant when you close this, current starts to rise. This, but what is the behavior of the coil? It opposes that sudden change in the current. Correct now? So what happens is a voltage appears across that. Clear? That drives a current. When current flows through this, you know what happens? A voltage appears across this. IR. As the voltage appears across this, you can expect the voltage across this decreases. So, in the passage of time, what you expect is finally all the source voltage will appear across the resistor. That means after that, this is simply a piece of wire without any resistance. No. If you apply Kirchhoff's law, what can you say? Applied voltage minus the voltage across them should be equal to IR. Do you agree? Or L dI by dt plus IR is equal to I. Yeah. At the instant when you close this G1, current is 0. So this factor becomes 0. So that dI by dt is E by L. What this case is the range of current determined by the applied voltage as well as the inductance. Larger the inductance, slower is the growth. You see? Larger the inductance, slower is the growth. Smaller the inductance, faster is the growth. At any other time instant, you can say dI by dt is equal to E by L minus IR by L. Correct? At any other time. That means what it says, as the time goes on, this increases. This factor increases, this quantity decreases. So the growth rate with the current rises, decreases. After some time, this becomes 0. The current will have reached a constant value. For the constant values calculated, you have E by L minus IR by L equal to 0, which means all the source voltage will appear across the resistor. The inductor plays no role on it. It is simply a piece of wire with 0 resistance. So one way of looking at the behavior of an inductor is at t is equal to 0, when you close the gate, it offers infinite opposition, isn't it? After a sufficiently long time, it offers 0 opposition. This is a first order differential equation with variable separated type. You know how to solve this. We have seen a similar equation in the case of CR circuit. Should I solve it? Can you do it? What you do is you write it as E minus IR on this side. Bring it down. dI by E minus IR is equal to dt by L. Integrate that. You can put in boundary condition. You can write it as 1 minus e power minus RE by dr. E by R is of course the maximum current. So this you can write it as R. As you can see, the current grows exponentially. Correct? As time goes on, you plot a graph of time versus current. Just reach the maximum grows. T reaches infinity or minus infinity. What is the dimension of this? Not more time. So the best thing is find the. This is in Henry. This is in ohm. V is equal to L di by dt. So Henry is volt second by amp. You follow what I got that? V is equal to L di by dt. So L is V dt by di. Divided by ohm. Ohm. You can leave it as ohm itself. Ampere into ohm is V equal to IR. Volt. That volt cancels. That shows that L by R as the dimension of time. It is actually called as inductive time constant. Inductive time constant. As in the case of capacitor, you can show that when P is equal to tau, for example, I is equal to I naught, and now we have where, now we have it is equal to, correct now? You have R by L. Here I have taken the denominator. When E is equal to what is the current? E is the native inverse. 1 by E is, you know how much it is? 0.37. 1 minus that is 0.63. So it is defined as the time needed for the current to grow to 63%. Now what you do is put this in contact, wait for about 5 time constants, so then the current will have reached the maximum constant value. Now put this in contact. Important thing is you have to see that the battery gets disconnected. Otherwise, it will be directly making a contact between positive and negative that may spoil the battery. Of course, put this in contact with this, it starts, the current starts decaying, and you know you can solve that simply put right hand side equal to E equal to 0. You get the expression for current as I is equal to I naught equal to minus. Correct? Solve the current E is. In fact, you can look at the here, for example, you can multiply every term by I. EI is the power supplied by the battery. I squared R is the power that gets dissipated in the resistor. Li di by dt is the power that gets stored in the inductor. Which, of course, if you integrate from 0 to I, you get it as half an answer. Correct? Clear? I did not go into the integration part of it now. Now, take down the problem. calculate the ratio of time constant in the build-up and decay in the circuit. Show. Calculate the ratio of time constant in the build-up and decay of circuit. Show. Come on, be the idea. What is the ratio of time constants in build-up and decay? How much? Yes, 3/2. Right. How do you do this? When you close this, the current builds up, but this path resistance doesn't play any role for the growth of current in this path, correct now? So, if T1 is the time constant for the growth of current, that should be equal to L by 2R. Do you agree? Do you agree? During the decay, you disconnect this. No current will flow in this. Now the current will flow. Correct now? What is the time constant for the decay now? The total resistance is VR. So T1 by T2 should be equal to allowed. In the circuit shown, initially switch S is open. The switch S is closed at T is equal to 0. Switch S is closed at T is equal to 0. Calculate the difference between the maximum current and minimum current that can flow in. Calculate the difference between the minimum current and maximum current that can flow in. One amp is the right answer. How do you get it? See, current is maximum. After a sufficient time after you close the key, because this will not play any role, correct now? This will act as a part of zero resistance. So you have closed this after a long time. There is a current flowing in this path. There is a current flowing in this path. So what is the total current? You can find the effective resistance. EMF by how much it comes to effective of this is 5. 10 by 5 is When? When is the current minimum? At the instant when you close it, because this offers this current will therefore be flowing through this. So what is I minimum when? 1 amp. So what is the difference between the two? 1 amp. Hello? Now suppose the EMF of the battery in the circuit varies with time such that the current is given by I, a function of time is 3 plus 5t, where of course the current is in amp and t is in seconds. Find the EMF for the battery as a function of time. EMF is varying with time. Your problem is to find how it varies with time, because you know current function with time. What's the answer? 42 plus, yeah. What's the answer? How do you get it? E equal to IR plus LDI by dt. What is right? 3 plus 5t. R is 4 plus L is 6. What is di by dt? Di by dt is 5. Clear? Okay, next. Find the value of I1 and I2. One immediately after S is closed. Immediately after S is closed. Too long time after S is closed. Long time after S is closed. Come on.
Immediately it's 3.33.
Immediately after S is closed, I1 is
3.33.
What about I2? I1 and I2 are equal, both equal to 10 by 3 amp. Correct? Perfectly correct. Then, long time after S is closed.
I1 is 2.5 and I2 is
Long time after yes is closed. See, immediately after S is closed, this will be offering infinite opposition. So current will flow through this only. So I1 and I2 are equal, same now. So what is that? Is equal to total EMF by total resistance 100 by 30. Yes. Long time after S is closed. What the answer you get? 100 by 22. That is I1. I2 60 by 10. Yes. A long time after S is closed, this is a path of zero resistance. So these two are in parallel. Find the effective of that. That is in series with this. What is the current starting? That is I1. Once you know that current, what is I2? Branch current formula. Main current into resistance is the other branch divided by sum of the resistance. Clear? So, when inductors are there in the circuit, you know how to analyze the problem. This is an IIT problem. Last in 2004. See, in the circuit, A and B are two cells of same EMF, capital E. Okay? But their internal resistances are different, R1 and R2. With the condition R1 greater than R2. Okay? Find the value of capital R such that PD across the terminals of the cell A is 0 a long time after the key S is closed. PD across A is 0. This is. Find the value of capital R. You have to express this capital R in terms of small r's. Find the value of capital R such that the PD across the terminals of capital A is 0 a long time after the key S is closed. Exactly correct. What's the answer? 4 by 3 R1 minus R2. Anybody wants me to work it out? C, he says a long time after the key is closed. How this behaves? It will be it offers a path of zero resistance. Correct now. A long time after, this will be an. That means this and this are connected simply by a piece of wire without any resistance. So what is the total resistance of the external resistance? How much? 3R by 4. What is the total resistance of the circuit? Plus R1 plus R2. Correct now? So what is the current in the circuit? E by 3R by 4 plus R1 plus R2. What is the EMF? What is the PD across A? PD across A is B minus IR1. This he says is 0. No. Simplify this, you get that. What is that? R is equal to, what answer you get? R is equal to
4 by 3 R1 plus R2.
Clear? This is an IIT problem which was asked in 2001. In fact, you can treat this as the resistance of the winding of this system. He says L is equal to 400 millimeter. Okay, R1 equal to 2 ohms, R2 equal to 2 ohms, E is equal to 12 volts. He says internal resistances are negligible. Battery is supposed to have zero internal resistance. The switch S is closed at T is equal to 0. What is the potential drop across L as a function of time? This one. What is the potential drop across L as a function of time? Of course, second part is there, in that you can write as homework. After the steady state is reached, the switch is open. What is the direction and magnitude of the current through R2 as a function of time? That you write later. Here you just try first part. What is the potential drop across the inductor? It's the practical inductance. If you take, what is the potential drop across its L? Got the answer? What's the answer again? 12 e to the power? Yes, that's the answer. Correct. Everybody wants me to work it out. See, what is the current in this? I is equal to I naught. Okay? I naught, you can say, into 1 minus e power minus RT by L. Do you agree? Or this current, I will call this current, say, because it is branching, I will take this as I1, take this as I2. So that makes it I2 is E by R2. I2 is equal to E by R2, 1 minus RT, R2 by L. Okay. What is I2 R2? That is E into 1 minus E power minus R2 T by L. Do you agree? This I2 R2 is nothing but the voltage across the resistor. No? Correct? So what is the voltage across the inductor? Voltage across the inductor plus voltage across the resistor is equal to the source voltage. So voltage across the inductor should be equal to source voltage minus voltage across the resistor, which is correct? Substitute the values. Hello? We now need to take up problems on mutual inductance. You know what is mutual inductance? When you have two coils which are linked magnetically, a changing current will produce a changing magnetic flux around it that gets linked with the other coil. You can call it as secondary coil. A current changing in the primary induces a voltage in the secondary. This phenomenon is what we call mutual induction, and the property of the coil, pair of coils, is what we call mutual inductance. Of course, it depends upon number of turns involved, depends upon the geometry, depends upon the permeability of the medium over which these two coils are bound. In fact, we speak of the closeness of coupling. For tight coupling, we say mutual inductance is, I think, root of L1 In other cases, it is defined as F is equal to some. The K is what we call coefficient of coupling. The trick of finding the mutual inductance is similar to the trick of finding the self-inductance. How you find the self-inductance of a given coil? You find out what is the flux produced by the passage of current. You know phi is equal to Li. When I is equal to 1, phi is equal to L. Correct? No? The flux generated when unit current flows through the coil. Similarly here, you find the field produced by one at the other. Find the flux linked with the other. What is the flux linked when unit current flows? That is the mutual inductance. You might have already calculated the mutual inductance of some standard configurations. Have you not done it in your regular class in college? Self-inductance? That also you have not done? We will do that if time is available. Okay, next week we will try this. Now we will take up problems on mutual inductance. We will begin with some simple problems. When a current of 3 amps flows in a coil, one coil, a flux of, it's very simple, a flux of 2 into 10 to the power of minus 4 Weber is linked with the other coil. When a current of 3 amps flows in one coil, a flux of 2 into 10 to the power of minus 4 Weber is linked with the other coil. Find the mutual inductance of the path coils. Use phi is equal to mi, mutual inductance. No? So m is equal to phi by I. How much it comes to? 2 by 3, which is 0.67 into 10 to the power of minus 4, which is, you can write it as 67.23. Will you agree? Can't you see this formula in your regular class? I thought I could avoid discussing all those theories so that I can concentrate on problems. If you feel that I should discuss theory, then we have to take class till March. Will it be alright if I straight away get down to problems? If a current varies in a coil 1, as I equal to 200 E square. If a current varies in a coil 1 as I equal to 200 E square, a voltage of 8 volts is induced in coil 2. A voltage of 8 volts is induced in coil 2 at t equal to 1 second. Find the mutual inductance of the path coils. What formula you use? V equal to m di by dt. So m is equal to v by di by dt. How much it comes to? 2 into 10 to the power of? Yes, or 20 millihenry. You can say 20 millihenry. Square root of L1, L2. One can derive it actually. But we will not do that. One can show the relation between the M and L1 and L2. If they are tightly wound, we call it tight coupling. That means if all the flux generated around the primary coil is linked with the secondary, then you can show that M is equal to geometric mean now. Usually it is not there. That's why M is usually less than root of. Try this problem. Find the mutual inductance between the circular loop of radius capital R equal to 0.25 meter and a square loop of side small l equal to 1 centimeter. Square root of side small l equal to 1 centimeter. How do you do this? You can see that there is a current flowing that will produce a field at the center. You suppose the field to be uniform throughout. Okay? You suppose L to be very small compared to 1, so that you can suppose the field to be uniform throughout the area of the square. So what is the flux linked with the square? You can find out. That phi is equal to mi. So what is I? What is m? Phi by I. I is 1 for unit current flowing through the circular coil. What is the flux that is going to be? How much flux to run? You can give an approximate. Calculate it merely on it. How much? Minus 2.5 into 10 to the power of minus 10. We get. See, what you do is find the field at the center produced by the circular coil. What is that? Mu naught I by 2r. Will you agree? Mu naught I by 2r. That is the field at the center. What is the flux over the square coil, man? dA, which is mu naught I by 2r into L square. Will you agree? But you can write this as equal to mi. So what is m? Phi by I. Substitute the given data. Have you understood? This is the technique. Okay, try this. Find the mutual inductance between a long straight conductor and a small loop of area 10 to the power of minus 8 square meter. 10 to the power of minus 8 square meter. Placed at a distance x equal to 0.5 meter. Placed at a distance x equal to 0.5 meter. Come on. Exactly, unit in 3. Clear? So, for these kind of problems, you know how to attack. Only thing is you should know the formula to calculate the area of the loop. That it could be a triangular loop, it could be a square loop, rectangular loop, circular loop. Okay? We will try one last simple problem. After that, we'll go away. How much work has to be done? How much work has to be done to increase the current from 1.1 amp to 2.2 amp in a coil of self-inductance 250 millihenry? How much work has to be done to increase the current from 1.1 amp to 2.2 amp in a coil of self-inductance 250 millihenry? No need. 453.75 millijoules, which is 0.45 AS as right now. That's the right answer. How you find the work that needs to be done? When the current was 1.1, what was the energy stored in it? Half Li square. When the current was 2.2, what was the energy stored? Half again. Correct now? Correct? In the given LR circuit, of course, as an example, in the given LR circuit, if the key is closed up, in the given LR circuit, if the key is closed at t is equal to 0, at t is equal to 0, find one. Current in the inductors as a function of time. Current in the inductors as a function of time. 2. Total magnetic energy stored at any instant. The given LR circuit, if the key S is closed at t is equal to 0, find 1. Current in the inductors as a function of time. 2. Total magnetic energy stored at any instant. Come on. First you give me the current through L1. Then current through L2, then total magnetic energy stored. What's the current in L1, man? Yes. See, you take the current starting from the source I. Okay. Current in this. Current in this. What is the current? What is the main current? First you find main current. We had already seen the branch current formula. First, what is the main current? It is E by R 1 minus E power minus what? R T by L. What is this L here? L effective, correct now? Because there are two L's in parallel now. Have you understood? There are two L's in parallel, so it is E by R 1 minus E power minus RT by what is L effective, man? L1, L2, because they are in parallel. This is the main current. What is the current through L1? I1 is equal to main current into L2 by L1 plus L2, correct? We have already seen that. Okay. Substitute. It is I1 or IL1 is equal to I is E by R 1 minus E power minus R T L1 plus L2 by L1 L2 into L2 by L1 plus L2. What is current through L2? That is I2. Tell me, what is the current through L2? That is I2.
By R into L1 plus L2.
Yes, into 1 minus
E to power
R into L1 plus L2 T by L1. What is the total magnetic energy stored?
Half L1 L2 by L1 plus L2 E by R whole square E to the power minus R.
Yes, the whole square. Yes. See, total magnetic energy stored is half Li square. What is L here? L is effective I square. Correct now? This is half L1 L2 by L1 plus L2 into I square. Correct now? You square this. E by R the whole square 1 minus E power minus R T. Clear? Take down this circuit. In the LR circuit shown, if the key is closed at t is equal to 0, the LR circuit shown, if the key is closed at t is equal to 0, find one current in the battery as a function of time. Current in the battery is a function of time. 2. Current in the inductors as a function of time. 3. Current in the resistors as a function of time. Current in the resistor is a function of time. 1. Current in the battery as a function of time. Current in the inductors as a function of time. Current in the resistors as a function of time. Current in the battery is E by R, E into R1 plus R2 by R1 R2. R2 1 minus R R1 E power minus R R1 plus R2 into yes, that is the current to the battery, which is the main current. Correct now? Now, what are the currents through inductors L1 and L2? Same thing multiplied by L2 by L1 plus L2. Correct now? Current through L2, same thing multiplied by L1 by L1 plus L2. Current through R1, same thing multiplied by R2 by current through R2, same thing. Let's take up one simple problem on calculating the, say, mutual induction. I don't know if you have done this problem. Standard configuration, we have not done. Mutual inductance of a pair of circular coils, pair of solenoid. Problems we have not done. We have standard. Not here, I am talking about whether we have done it in school. Evaluate, we'll take one interesting problem. Evaluate the mutual inductance between a rectangular loop. Evaluate the mutual inductance between a rectangular loop and a long string wire. You have a long straight wire. There is a rectangular loop. What is the mutual inductance between them? This is. We'll take the dimension of this and say this is A. This is B. We'll take this distance as C. Tell me how you can do this. Take us with the so take a strip as you said, right? At what distance we will take it as? Some R, say, okay? Find the area. Imagine that there is a current flowing. We will take the current flowing down. Okay? What magnetic field is produced at this location? What is the flux? Correct now? Integrate that. Flux per unit current will give you the mutual inductance. You are doing. That's the trick of finding the mutual inductance. mu1 A by mu0 A by 2 pi log B plus C by C is the right answer. Yes. Bravo. Anybody wants me to work it out? Simple integration.
Questions on solenoids.
Solenoids,
Yeah, we should put it in the class. Solve it.
So what parameter the solenoid? Mutual inductance, self-inductance. Ampere's law.
You just give the degree. You can write and check that out.
Oh. Let's try this one last. Draw this. Try it as an assignment problem. A small square loop of a wire, side smaller small square loop. The wire of side small L is placed inside a large square loop. Placed inside a large square loop of side capital L. Inside the bracket you write capital L is much greater than small l. If the loops are coplanar, what do you mean by that? They lie in the same plane. If the loops are coplanar and their centers coincide, what is the mutual inductance of the system? What is the mutual inductance?